Good morning, ladies and gentlemen. Welcome to Topic 9. We today are beginning Topic 9, which is all about solving quadratic equations. So in Topic 8, we learned about all of the different characteristics of quadratics and how to graph them and what the vertex means and the axis of symmetry, and how to use quadratics in some sort of real life situations, and we also compared quadratics to linears and exponential functions. Now we're going to look at what it means to actually solve quadratic equations. There are many different ways to do that. In fact, in this topic, I believe there are 6 different ways that we can solve quadratic functions. And so we're going to talk about what does it mean to solve quadratic functions today, what does that look like, and specifically we're going to talk today about how we can use graphs to help us solve quadratic equations. Now notice your homework is 361, 362, numbers 13, 16 through 22, and 28. You can go ahead and use Desmos today when you are graphing your quadratic equations, because we did learn graphing last topic, and you won't be graphing other than in this topic and the last one. So let's begin by defining a few things. Hopefully you did the explore and reason at the top of the left hand side, and then you taped in or wrote out this piece of information. These are the vocabulary words that are extremely important for this topic in general. We're talking about it in 9.1 because this is the first method of solving, and it's important that we get these vocabulary words down because we're going to use them for the rest of the topic. So when we were talking about solutions to equations, this is any type of an equation, what we're looking for is the value, or sometimes values, there could be more than one, that make the equation true. So for example, when we would solve for x in any linear equation, we'd get one number that made the equation true. If we got something like 2 equals 2, then we knew that any number could fit into that equation and make it true. In quadratic equations, there are usually 2 solutions. Now, not always. There could be no solution, there could be one solution, but most of the time we find that there are 2 solutions. The reason there's 2 solutions is because a quadratic equation is an equation of the second degree. Okay, so because it's of the second degree, we usually have 2 solutions. Now, the zeros of the function are actually the solutions. So if I tell you to find the solutions to the quadratic equation, or if I tell you to find the zeros of the quadratic function, that's the same thing. The zeros of the function are the solutions to the equation in the form f of x equals 0. Now, what this looks like is the x-intercepts. What x values make y equal to 0? So if we look down here at this parabola, the zeros of the function are these 2 points here, the x-intercepts, They occur when this function, f of x equals x squared minus 16, is equal to 0. They set it equal to 0, graph it, and these two values are the solutions. So it's these two numbers, or these two solutions, are the value or values that make this equation true. So if I plugged in -4 to this equation, I should get 0 equals 0. Let's try it. -4 squared minus 16 equals 0. Well, -4 squared is positive 16, and 16 minus 16 is 0. So it works. If I plugged in 4 squared is also 16. 16 minus 16 is 0. So it also works. So we know that these solutions are to this equation because when we plug them in, we get a true statement. Okay, so what you're going to be asked to do today is find zeros of particular quadratic equations. Now that's going to look different. However, we're going to do one example with 3 parts that's going to kind of go over that for you, and then we're going to do one more real-life application of this. So if we're going to find the solutions of x squared minus 14x plus 49 equals 0. So we want to know what x values do we plug in here to get the y values equal to 0. So what are those x-intercepts? Now, in this lesson, we're using graphing to help us solve this problem. In order to do that, because it's in standard form, I want to find the vertex first. So I'm going to say x equals negative b over 2a. Learn this in topic 8. Negative b is negative 14 over 2 times a is 1, so over 2. So 14 divided by 2 is 7. And then I'm going to plug that back into the function to get out my y value. So y equals 7 squared minus 14 times 7 plus 49. I'm going to plug that into my calculator, and I get 49 minus 98 plus 49, which equals 0. So my vertex is this ordered pair 7, 0. So I'm going to graph that. Of course, I run out of room, so I'm going to go by 2's. This here is my vertex. What do you notice about that vertex? It's actually on the x-axis. So no matter what my parabola looks like, I know it opens up because my a is positive, but no matter what it looks like, it will only cross the x-axis at that vertex. So when you get a vertex that's on the x-axis, this quadratic has one solution. And that one is this ordered pair 7, 0. Now, what if we found the solutions to x squared plus 3x plus 7 equals 0? Okay, so again, I'm going to do the same thing because this is in standard form. I'm going to use vertex formula to find my vertex. and determine whereabouts that's located on my graph and see if there's something that it tells me about it. So x equals negative b over 2a. My b is 3, so negative 3 over 2 times 1, which is 2. So it's either negative 3 halves or negative 1.5. It's easier for me to plug in decimals, so I'm going to do that. Y equals negative 1.5 squared plus 3 times negative 1.5 plus 7. That equals 2.25 plus negative 4.5 plus 7, which equals 4.75. Okay, so my vertex in this case is negative 1.5, 4.75. Okay, so my vertex is way up here. However, this quadratic also opens up because my A is positive. Because that is the case, no matter what the width of my parabola is or what it looks like, other than opening up, this will never hit the x-axis. So this problem has no solutions. Because it will never cross the x-axis. It does not have any x-intercepts. Okay, so now we're going to do one that actually has solutions. Well, it has two solutions. Okay, so find the solutions of negative 4x squared plus 4 equals 0. So again, I'm going to find the vertex, and then I do have to actually find the points around it because that's how I find the zeros. So I'm going to start with x equals negative b over 2a. There's actually no b in this one, and so it's 0 over 2 times negative 4, which is 0. So I'm going to plug 0 back in. Y equals negative 4 times 0 squared plus 4, which equals 4. So my vertex is this ordered pair 0, 4. So I'm going to draw that over here. 1, 2, 3, 4. And then remember when I'm solving these, I have this axis of symmetry here, so I'm going to plug in 1 point next to it and see where that gets me. If I plug in 1, remember, then I can reflect it over the axis of symmetry. 1's an easy number, so I'm going to plug in 1 for my x. Negative 4 times 1 squared is negative 4 plus 4. That equals 0. So my ordered pair is 1, 0. That is one of the solutions. And I can reflect that over the axis of symmetry. So my other solution is negative 1, 0. So when it crosses the x-axis twice, there's two solutions. One, 0, and negative 1, 0. Now, I want you to pause the video here for just a minute, and I want you to look at example 3 on enVision. Read through that, and then we're going to talk about it just briefly here in our notes. Example 3, and I skipped example 2, but example 3 has a function f of x equals negative 5x squared plus 25x plus 1. And basically what it's saying is to use the graph to help you determine how long the ball is in the air for. Now, if you graph this function on Desmos, I highly suggest you do that and look at what it looks like. And you can use the scroll feature on there to look at the different values and the different ordered pairs. But basically what you will see is this function starts at 1, that's the y-intercept here, and it's in this parabola shape. And what you see, this is the height, and this is the time in seconds. Okay, as you're scrolling on Desmos, you see this ordered pair here is 2.5 and 32 abouts. Okay, so it takes from 0 to 2.5 seconds to reach the maximum height. So at that point, the graph is turning around and coming back. Remember that this is symmetrical. So if this is 2.5 seconds, then this must also be right about 2.5 seconds. So this, it should be about 5 seconds for the ball to come back down, because it's symmetrical from here to there and then there back. So that is your solution.